Okay, shout out to SB. We missed her today. Is anybody else gone? Josie? Mr. Josie? Maya, we missed you when you weren't here. Lauren, we missed you when you weren't here. He's... the Phantom. Okay, one of the applications of derivatives is related rates of change, which you guys have just used. Here's another type of application, and we call it linearization. Linearization has this idea. If you were to take a function, we'll call this f of x. Everybody agree that f of x is not a line? Okay, but if you look at it in very small windows, so for example, suppose that you looked at this window right there. It kind of looks like a line, right? And if you consider, say another window, say you consider this window right there, that small little window, it kind of looks like a line there, doesn't it? In fact, if you zoom in close enough on any function, you could think of it as an infinite set of lines. And so the linearization of a function is as you get really close down into that function, you can start to kind of make it into small little lines. So what we want to do is we want to write a formula for the linearization of a function. What we do is we talk about a point. We'll call this x sub 0. And this is going to be f of x sub 0. And in order to write an equation for a line, you need two things. What do you need? A slope and a point on the line. So as I call this point P, what is our coordinate for point P? X sub 0, f of x sub 0. How do I determine the slope? Take the derivative. So f prime evaluated at x sub 0, that's the slope. So as we plug that information in, y minus y1 is equal to m times x minus x1, what we have is y minus my y1 value is f of x sub 0 equals m is f prime of x sub 0 times x minus x sub 0. Or in other words, y is equal to f prime of x sub 0 times x minus x sub 0 plus f of x sub 0. So the idea is you can take really any function that you can find the derivative of, and you can linearize it. You can look at a small portion and make it into a line. Why is this helpful? Why is it useful? It helps us evaluate difficult functions in small spaces. So the first thing we're going to do is we're going to find the linearization of two functions, and then we're going to apply it to a problem. And so all we have to do is get through example 2, and you'll be done for the day. Okay? So find the linearization of the function. You've done this many times. The only difference is we're just trying to review it, and you're now understanding it as a linearization within a small window. So in order to find linearization of a function, you need slope, and you need a point. What is our point? 1. What is the y value? 3. How do I determine the slope? What is the derivative? What do I plug in for x? 1, and I get a slope of 8. They're crazy. All right. All right, so y minus 3 is equal to 8 times x minus 1, or y minus 3 is equal to 8x minus 8. Y is equal to 8x minus 5. Now, I want to be clear so that you understand what we found, okay? Do you know what that graph looks like? Okay, so here's what we've determined. That this line, which is tangent at a value of 1, so I'm just going to draw this graph right here. As you move further away from 1, it's not a very good estimation. But when you are close to 1, 4x squared minus 1 is approximately the same as 8x minus 5. Those are very, very similar within this small window at x is equal to 1. So if we would move 100th to the right or 100th to the left, these are pretty good approximations for each other. However, if you were to move, say, 10 to the right or 10 to the left, they would not be very good approximations of each other. And you're going to see how that plays out here in just a second. Okay, what's different about this one? Okay, so we're going to review some trig here. So I first need a point. What's the x value? How do I calculate the y value? Plug it in. 2 times pi over 2. Pi sine of pi. 0. Yep. Got to find the slope. How do you find the slope? Derivative. How do you find the derivative of negative sine of 2x? Chain rule. Negative sine of u and 2x. Derivative of negative sine is negative cosine. So therefore, the derivative is negative 2 cosine of 2x. What do I do now? Plug in pi over 2. So 2 times pi over 2 is pi. What's the cosine of pi? Negative 1. Negative 1 times negative 2. 2. So y minus y1, y1 is 0, is equal to m times x minus x1. Or y is equal to 2x minus pi. So that's approximately the same as negative sine of 2x at x equals pi over 2. No, I just want you to understand what this means. The idea is that if you plugged in a value for negative sine of 2x, you might say, well, I don't know how to find the sine of something without my calculator. Well, as long as you're really close to pi over 2, you don't have to use that. You could just do 2x minus pi. See, this is a lot easier to work with, isn't it? Let's go to the real example that you want to be able to follow along with. Find the linearization of the function f of x equals square root of 4 minus x and use it to approximate the values of square root of 3.99 and square root of 4.1. We're going to approximate the square root of 3.99 and square root of 4.1. If I told you find the square root of 3.99, what would you do immediately? Take your calculator. I want you guys to go back in time and consider this. People such as Isaac Newton and others, back when calculus was formalized in the year 1600 or so, they used to do these problems without a calculator at all. Okay, so when you look at calculus sometimes you have to think about, what would I do if I never had a calculator? Think about these people who would be trying to do mathematics, no calculator ever. Okay? how would you even start coming up with the square root of 3.99? You know what you do? You say square root of 3.99, it's about 2. Yeah, you'd say, let's go 1.9999. Yeah, let's just, and they would say, let's become more accurate than that. So we'll see. I start by finding the linearization of the square root of 4 minus x. Now, this is where people start to get confused. Square root of 4 minus x. Do you remember what that looks like? Shifted to the right 4 units, and it heads back this way, correct? Now, we're choosing to use the square root of 4 minus x, because if you plug in 0 for x, you get the square root of 4, correct? And that's very close to these two, isn't it? See, we're choosing a function that gives us a value very close to these. That's the whole goal, okay? So I want to start by finding the linearization. So I need slope and I need a point. It doesn't give us a point, does it? Guess what? You have to choose a point. Why 0? Because 4 minus 0 is, and that's really close to 3.99 and 4.1, right? Also, if we plug in 0, can you find the square root of 4 minus 0? What is it? 2. Second part, we need to find the slope. In order to find the slope, we take the derivative. On the outside, I have u to the 1/2. On the inside, 4 minus x. Derivative 4 minus x. -1. Derivative of u to the 1/2. So I get -1 over 2 roots of 4 minus x. What is the x value that we are using? We're using 0. Let's plug in 0. I get 4 minus 0 is 4. Square root of 4 is 2. Times 2 is 4. I get -1/4. So it turns out that I have y minus 2 is equal to -1/4 times x minus 0. Or y equals -1/4 x plus 2. That's the linearization. It's the tangent line. We are now going to make use of it in the context of this problem. What do you notice about the line? It always sits what? Above. So therefore, the line is always greater than the actual function. Would you agree? Okay, we're going to use that in a second here. So I want to approximate the square root of 3.99. The square root of 3.99. Okay? Is approximately equal to, what value would you plug in for x so that you had 3.99? 0.01 or 1 over 100? So I'm going to take this function, -1 over 4, and multiply by 1 over 100, and then add 2. And when I do that, I get negative, Cloudwing comes in, -1 over 400 plus, if I write 2 with a common denominator, what would it be? 800? And I get 799 over 400. So the question is 799 over 400, is that a close approximation to the square root of 3.99? Watch. Square root, hey, get out of there. Square root, 3.99. You are horrible. You are horrible. I am Look at our approximation. That's pretty close, isn't it? Yeah. So Isaac Newton and the others, they have a great way to approximate the value of square root of 3.99. You should be able to do that without a calculator. Let's try. Yes. What's that? Oh, how does a calculator come up with this? That'll I'll have to show you some other time. But no, your calculator does not do that. It uses a different algorithm. Last one, square root of 4.1. What would you plug in for x to get the square root of 4.1? Negative 1/10. So that's approximately equal to negative 1/4 times negative 1/10 plus 2. What's negative 1/4 times negative 1/10? 1 over 40 plus 2. Common denominators? One over 40 plus 80 over 40. And I get 81 over 40. Let's check and see how that turns out. Square root of 4.1. And I'll try 81 divided by 40 and see if I get something close. I think that's pretty good. The last question is, are these overestimations or underestimations of the actual answer? They are overestimations. Why? Because this function always sits above the other function.